Okay, we are in our thermodynamics chapter. I think we're back up to 16. So last time we started talking about thermodynamics, and we talked about entropy to start with, and entropy, a different letter that we got to use, which is delta S. And entropy does work a little bit sort of different in a sense than delta H does. Entropy has to do with the amount of disorder or order, however you want to look at it. And actually, when the amount of disorder increases, so does the entropy value. It becomes more positive. And vice versa, if the amount of disorder starts to decrease, which means obviously the amount of order will increase, we have a more negative value there of entropy. In terms of units of entropy, typically they are joules. And one way that you can calculate the entropy is really the same way you can calculate any thermodynamic sort of property, which is take the delta S of our products minus the delta S of our reactants. And these would be obviously table values that you would look up in a table, like you would look up, for example, delta H values or things of that nature. You do want to always, when you do go to those thermodynamic values and tables, you want to always make sure that you find the substance that you're looking for, and also make sure that you find it in the correct state. Now, delta S is also a little bit different, as we'll see. They are typically in joules, and they are typically positive values. The reason I mention that is, as we'll see in this chapter, there is equations where delta H, which is our enthalpy, is also used with delta S. And again, enthalpy is usually in kilojoules. So once again, you got to watch those units, especially when we get into some of those formulas where we do use them together. We talked about sort of at the very end there, the idea of a probable event or an improbable event, and really the Boltzmann type equation, where the entropy is equal to K, which is the Boltzmann's constant, natural log of S, no, natural log of W, which is the number of microstates. So remember that if there is sort of a ordered way or one way of doing something, it's sort of an improbable event, and it'll probably have a low entropy value. If there's many ways to do something, there's going to have a much higher sort of entropy value. So if you remember, I think we had circles and boxes, and if you want to put them all into one box, there's really only one way to do that, which means the natural log of 1 would equal 0, which means our entropy would equal 0, and it would be a much lower number than the one where we had obviously an opportunity to put 2, I think, circles in each box. There's like 6 different ways you could sort of accomplish that. And again, if you take like the natural log of 6, you'll get a much higher number, obviously, and would give you a much higher entropy value. Any questions on that stuff there? One of the main things that we look at in terms of that's really sort of easy to sort of visualize the change in entropy is when we change states, right? As we go from solid to liquid, there's a lot more movement in the liquid phase, which means the entropy is increasing. And as we go from liquid to gas, the entropy increases a lot more, because as we go from liquid to gas, everybody's breaking apart from one another. They're flying around crazily, right? So that creates a lot of disorder that's sort of happening, and a much, much higher disorder as you go that way. As you go the opposite way, obviously you'll be decreasing the disorder and increasing the order. So let's continue on then. These are all processes that lead to an increase in entropy, which would mean we'd have more of a positive number. So as we just talked about, the sort of phase change is very common. In solid states, usually things are very well organized and arranged. They have long range order, especially like things like ionic solids have really long range order. As we start getting into that liquid stage, as we've been talking about, we have a lot more room for movement, a lot more disorder sort of happening, a lot more energy sort of happening. And then obviously that big jump there from liquid to the gas phase going to create a lot more disorder. Making a solution is also an increase in entropy type of situation. It's actually for both things, or both parts of a solution, both the solute and the solvent. Remember the solvent, say something like water, before you dissolve something in water, it's really organized, right? All the water molecules are bonded together through hydrogen bonding. It's pretty much nicely organized. And then if it's an ionic solid that you're going to be dissolving as a solute, as we can see on the very top there, it's very organized. So in order to get all these guys kind of come together, we got to break bonds, move things around. And then now we have obviously a lot more mixture of everything, a lot more disorder has occurred. Lastly, temperature obviously can play a big role in terms of disorder. Obviously, when things increase their temperature, in addition to increasing their temperature, that usually also means that there's some type of input of energy, which means whatever is there is going to pick up a lot more energy. And for example, if we're talking maybe about a gas molecule or any type of molecule, really, it's going to start moving around a lot faster, creating a lot more disorder that's going to happen in that situation. Any questions on any of those there? All right, so for each of these, take a moment and decide how the entropy of the system will change for each of these processes. Will the entropy increase? Okay, let's take a look at these. So first one, we're going for condensing water vapors. So condensing means condensation, and that is basically going from gas back to liquid. So definitely we're going from gas, which is a lot of disorder, everybody flying around, to liquid, where obviously they're much more closer to one another, not moving around as much. And that's going to decrease the disorder, right? Which means the entropy should also decrease and should be positive or negative, the change in entropy here. Change in entropy should end up being negative in this case, as it's decreasing. Or if you want to look at it the other way, you're increasing the order, and that would cause a decrease in the entropy. Forming a sucrose crystal from a supersaturated solution. So in order to form a crystal, crystals are pretty well organized, right? Ordered type of solids, which means clearly you're increasing the order, decreasing the disorder also in this one. So once again, disorder going down, entropy change would also be decreasing. And once again, we would expect it to be a negative change in entropy in this particular situation. As we heat hydrogen from 60 to 80, that should do what? Should that increase the disorder or decrease it? Should increase it. Again, increasing the temperature here is going to make those gas molecules pick up a lot more energy, going to increase their velocity, going to have them flying around a lot more crazily around your face if you're near it, maybe not. And that would increase the disorder. That would obviously increase the entropy change. And in terms of the change in entropy, we would expect more of a positive change that should come out of that. And lastly, subliming dry ice, that's sublimation. That is where we go from, not there, we go from solid to gas directly, skipping the liquid part. So that clearly is increasing the disorder as we end up in the gas phase. And that's going to increase the disorder, increase the entropy, and going to see, again, a more positive value. So again, as we talked about last time, sometimes it's hard for people, especially after coming off of delta H's, where we kind of think of like negative values as, you know, exothermic and things happening. But again, here with entropy, the more positive the value, the more increase we have in that disorder. Any questions on any of those there? So entropy, much like energy, as we saw earlier, they are state functions, like our hikers there. It doesn't really matter, you know, how you get there. But once again, like most thermodynamic sort of properties, the two really main things are where you end and basically where you begin. And as we talked about last time, our reactants in a chemical reaction is where we begin, and our products, right, is where we end in a chemical reaction. So obviously, as we talked about, you can calculate the delta S of the reaction just like we could do with any of the other thermodynamics by taking our delta S of our products minus the delta S of our reactants. Now, if you are only given an equation or the equation in words, whatever it may be, and you're asked to calculate the change in entropy for that, that basically is the formula that you should use to calculate the entropy. You would go to a table such as this one here. You could look up the entropy values. And as we mentioned before, major difference there. These are going to be joules and they're going to be positive values. Another major difference that we see in the entropy table that we do not see in the enthalpy or delta H table is things in their standard states that's not combined in the enthalpy table for delta H of formation are zeros, but there are values for entropy here for things in their standard state. So things like O2, N2, just like a metal by itself, you will actually find values for them in the table. By the way, when we do this calculation, obviously, as we will see, we also still take into account, obviously, the coefficient and make sure we multiply it by it as well. So when we look at entropy, which is sort of the second law of thermodynamics, the first law is what we were talking about with the conservation of energy, which is obviously energy cannot be created nor destroyed, but can be obviously transformed from one place to the next. The second law of thermodynamics is the entropy of the universe is increasing in a spontaneous process and remains unchanged in an equilibrium process. So when we actually use sort of entropy to try to determine whether or not a reaction is spontaneous, and again, a reminder that when we talk about a reaction being spontaneous, it has really nothing to do with how fast or slow the reaction is occurring. Again, just means that under those conditions, that reaction should occur. We actually need to use what is referred to as the delta S of the universe. And the delta S of the universe is basically made up of two parts. It is made up of the delta S of the system and the delta S of the surroundings. And the delta S of the system is also sometimes the delta S of the reaction. As we talked about, basically, the reaction that we're interested in is our system in most cases. So if you're doing something in a test tube, that would be your system. And then obviously everything else outside of that would be your surroundings. And if you do calculate the delta S of the universe and it is a positive number, then that reaction would be spontaneous, which basically means for the most part, the way it's written, it should head obviously from reactants to products, how it's written. Obviously, the opposite would be true if you calculated delta S of the universe and it was a negative number, then that reaction would be non-spontaneous the way it's written. If you calculate delta S of the universe and it does equal 0, it's an equilibrium process, which means it's already kind of done. There's not much happening, right? It's kind of going back and forth at the same rate. So there's not much change is going to occur in terms of that system. So how do we calculate each of these things, both the system and the surroundings? There's actually a couple different ways or different ways that we do each of these things. So let's start with the delta S of the system, which is also sometimes the delta S of the reaction. And let's go back. So to calculate the delta S of the system or the reaction, we basically will just look up the values in the table. And as we talked about, we will take all those values, make sure we multiply them by the coefficients and basically add up all the delta S for our products minus all the delta S for our reactants, and we can calculate the delta S of the reaction. This little knot here is what is sometimes referred to as sort of a knot, but it's referred to basically what it means is sort of standard conditions. So a lot of times this is sort of table conditions. And when we talk about standard conditions for sort of thermodynamics and most sort of table values, that means that usually sort of standard conditions is 1 atmosphere if we're dealing with some type of pressure. It's 1 molar if we're dealing with some type of concentration. And the temperature is 25 degrees Celsius. So these are typically the sort of values that are the conditions that happen when we do have a table type value. And that's usually what that means is you're kind of doing it under sort of standard conditions is one way you can kind of think of it. So if we wanted to calculate the standard entropy change for this following reaction, why don't you give it a go, see what you come up with. These would be obviously the values that you could find from the table. I feel like I'm missing one there. All right, let's take a look at, so once again, a lot of cases, they will not be provided for you. So you will need to go kind of look them up there in the table. But once again, we're going to use our delta S of our reaction, again, the delta S of our products minus the delta S of our reactants. So put it in on our product side. Again, we do need to take the 2, which is the coefficient there, and multiply it by the value of CO2, which was 213.6 joules. We are then going to subtract it from our reactant side, which is 2 times the value of CO, which is 197.9. We're then going to add it to our other reactant here, which again, unlike delta H, we will find a value for O2, and that value is 205 joules per Kelvin per mole. Putting all that together there, maybe a minus 173.6 joules per Kelvin, if you like. First off, any questions on that? Does this number tell us if this reaction is spontaneous or not? This number does not actually tell us that. It just tells us in this case that the reaction is increasing disorder or decreasing disorder. This reaction, the order is decreasing. We could actually check ourselves by actually just looking at the equation itself, and we should have an idea as to whether or not, maybe not if our number is correct, but if our sign is correct. When we look at this equation in terms of gas molecules on this side, we started with how many? 3, 2, and 1. On the product side, when we were all finished, we ended with 2. So we went from a situation where there's 3 gas molecules flying around to a situation where there's only 2 gas molecules flying around. We increased the order, we decreased the disorder, and we would expect just from that situation that our value for delta S should be negative. Yeah. Any questions on that? So once again, we cannot use the delta S of the reaction to tell us if it is spontaneous or not. We do have to calculate delta S of the universe, which does require us to calculate, obviously, the delta S of the surroundings. So let's talk about maybe how to do that, which is, all right, in a second we will. So as we just saw, if a reaction produces more gas molecules than it consumes, we will get a delta S value that is greater than 0. And if we produce less gas molecules than what we started with, as we just saw there, we'll get a delta S value that is more negative. And if there is no change in the number of gas molecules, then it could be positive, it could be negative, but it will be relatively a small number or value that is there. So if we had to predict the sign of this particular one, the delta S sign should be positive, negative. What do you think? How many gas molecules are we starting with on the left? It is just 1. Yes, that's a solid. And on the right, we have 0. So we had 1 gas molecule flying around. We ended up with none, which means we definitely have increased the order, decreased the disorder, and we would expect the change in entropy to actually be like the last one, should probably be negative in this case, right? As we have increased the order. Any questions on that? So a lot of times in this sort of thermodynamics chapter, and we'll see it with a few more examples as we go through the chapter, sometimes you just ask these type of questions where they don't give you numbers or anything like that. They just go, hey, in this situation, would you think it is increasing or decreasing? So a lot of times you could kind of just look at what's happening in the reaction and make a pretty good educated guess as to is it increasing or decreasing. So now let's talk about the surroundings and how we could calculate the delta S of the surroundings. So if we look at this process here on the left, this is an exothermic process. This is the system releasing all that heat and energy to the surroundings. When the surroundings picks up all that heat and energy, what should happen to the entropy of the surroundings? Should it go up or should it go down? It should go up, right? So it's picking up all that energy, which is going to make the surroundings crazy, right? And wild and moving around. So we would expect an increase in the amount of entropy, which means the change in the entropy for the surroundings should actually become more positive. Opposite is happening over here. This is an endothermic reaction. So the surroundings are actually supplying some energy to the system. The result of that is the surroundings just lost a bunch of energy, which means they're not going to be moving around as fast, right? They're going to kind of slow down, and it's going to increase the amount of order that is there. And we would expect for the surroundings that the amount of order increases and the amount of disorder also decreases, which is the same thing. The delta S of the surroundings then would become more negative in that situation. So there is a relationship between the delta S of the surroundings and the delta H of the system. The delta S of the surroundings is proportional, is what that should be, to negative the delta H of the system. So what does that really mean? It means this. If we look at that, which is our delta H of the system and our delta S of the surroundings, and our delta S of the surroundings is equal to minus delta H of the system. If I have a exothermic process, my delta H value should be a positive or negative number. Should be a negative number, which means a negative and a negative will turn my delta S of the surroundings into a positive number here. And if I have an endothermic process, my delta H should be positive, which means if I put that positive in here, a negative and a positive will turn my delta S of the surroundings into a negative value. So it's basically an opposite relationship that we see for the delta S of the surroundings. Does the surroundings temperature play a role in the entropy change that we would see for the surroundings? Would the surroundings temperature have any effect on it in this situation? The answer is yes. And for example, let's say our surrounding temperature was like a super high temperature to begin with, right? And this reaction gives off some energy. Is that added energy going to make that much of a difference if the surrounding temperature is really high to begin with? Not very much, right? It's kind of like if you lit a match and you could feel the heat coming off. But then if you lit a match, and don't do this obviously, and put it into an oven that's really hot, right? And the heat coming off of the match based on the oven's temperature, not going to make that big of a difference to the overall energy that's happening in that oven. Again, don't put your head in an oven or anything like that, please. And don't light a match near gas unless you want to light something on fire. So the temperature of the surroundings does play a role as to the sort of entropy change that we would see in the surroundings. And again, if we had sort of a higher temperature in that surroundings, the increase of entropy that would happen from, say, an exothermic reaction would not be all that much. And obviously, if we had a lower temperature in the surroundings, we would see a much larger sort of effect on the entropy if we had sort of an exothermic reaction happening. So to calculate the delta S of the surroundings, I'm not sure what happened here. Hopefully it looks maybe better on yours, but the delta S of the surroundings is equal to minus the delta H of the system or the reaction divided by the temperature. And of course, our temperature here does need to be in Kelvin. Yeah. And that's because our delta H is here. Now, a reminder that typically speaking, delta S is given in joules, and probably the value of delta H that you will be given will be in kilojoules. So sometimes it's converted into joules for the ending product here. So we could calculate the delta S of the surroundings. We can then use our delta S of the reaction like we just did. And if we wanted to calculate the delta S of the universe, we basically just add those two numbers together. And that will allow us then to figure out whether or not a reaction would be spontaneous under those particular conditions. It is a negative there, and it's important that you remember that the negative is there. It's also important a little bit later on in this chapter here, we will see an equation that looks just like that without the negative. Yeah, so sometimes people get those kind of confused. So if you're doing surroundings, delta S of surroundings, definitely make sure that negative is there and try not to confuse it a little bit later on when we see that again. So I'm going to try one here, calculate both the delta S of the system, delta S of the surroundings, and determine whether or not this reaction is spontaneous at 25 degrees Celsius, given the information that you see up here on the board. Okay, let's take a look and see. So in this case, we want to calculate both things, our delta S system or the reaction and our surroundings. So I'm going to start with the system or the reaction. So our delta S here of our reaction, again, going to be really our delta S of our products minus the delta S of our reactants. So in this case, we have, again, we want to take the coefficient there. So that's going to be 2 times the table value there for NH3. Which is 193 joules, basically. Takes care of all of our products. We're then going to subtract it from our reactants. So we have 1 N2, which is 192 here. We're going to then add that to our other reactant, which is 3 of the H2, which has a value of 131. And that's going to give us here 2 times 193 minus 192 plus 3 times 131. Looks like we get something like minus 199 joules here. So we can again make sure that this number sort of makes sense. This number tells us we have a negative delta S for our reaction, which means we should expect the amount of disorder to decrease or the amount of order to increase, however you want to look at it. And again, we can kind of count up our gas molecules here. Left-hand side, we got 4 gas molecules. Right-hand side, we only have 2. So we are decreasing the disorder here, and that does make sense in terms of the sign that we ended up with, which is negative. Questions on that calculation so far? All right, and again, we can't really use this to determine spontaneity, so we do have to calculate the delta S of the surroundings, which we can do because they gave us our delta H of this reaction. So the delta S of the surroundings, once again, is minus the delta H of the reaction divided by the temperature in Kelvin. So a little 273 action on that there. Going to give us a 298 Kelvin. And we're going to put this in, and I'm going to go minus 92.6, and that should have one more minus, right? And I'm going to actually multiply this by 1,000 to convert it to joules because my delta S of the reaction's in joules. That way, everybody's in the same unit. Obviously, if you didn't do that, you would be in kilojoules and over 3 decimal places there in terms of your answer. So we're going to get 92.6 basically times 1,000 to convert it to joules divided by 298. Going to give us, we'll call it a 311. And again, this would be joules in this case. Obviously, if you left it in kilojoules, you would have 0.311-ish kilojoules. This also makes sense, right? If we think about what's going on here in terms of our surroundings, this reaction is endothermic or exothermic? This reaction is exothermic. Yes, we have a negative. That means this reaction is giving off heated energy to the surroundings. The surrounding temperature is just like normal temperature, kind of low. And that means that that added energy to the surroundings should increase the amount of disorder in the surroundings. Thus, we have a positive number here, right, for our surroundings. Any questions on that? Now, the convenience here of converting it to joules at this point is when I add them together, I'm not going to screw up by adding kilojoules and joules together and get the wrong answer. Everybody's in the same unit at this point. So to figure out the delta S of the surroundings, not surroundings, delta S of the universe, we're going to take the delta S of the system, our reaction, plus the delta S of the universe. We're going to add them together. So that's going to give us a minus 199 plus a 311. Once again, if you did not convert, you need to do a conversion at this point into one of the units, whatever way you want to go. But once again, S is usually in joules. So minus 199 plus 311. Going to give us a 112 joules positive in this case. Is this reaction spontaneous? This reaction is spontaneous as our delta S of the universe is a positive number. This is also an example of a reaction that is spontaneous, but really slow if you don't put a catalyst in it. Yeah. So again, it has nothing to do with how fast or slow. Yeah. It should be surroundings, but I think I wrote universe twice there. It kind of appears that way. So thank you. So got the S part right. So that should count, right? Partial credit, right? All right. Thank you. That should be surroundings. Thank you. Other questions? Okay. So this is obviously what you would want to calculate if you want to use delta S again to determine whether or not a reaction is spontaneous. And clear to do that, you would need to know the delta H of the reaction. If you don't know it, you might have to look it up. No pictures. Yes, thank you. So you may have to calculate like we calculate delta H in the previous chapter, products minus reactants. All right. Let's talk a little bit more about entropy before we move on to a different letter of the alphabet. And that is the third law of thermodynamics, which is some of the stuff that we've talked about. The third law of thermodynamics is the entropy of a perfect crystal basically is 0 at absolute 0 temperature. And we do have entropy of phase changes that do occur. And obviously this is our Boltzmann equation we saw earlier. And obviously, as we've been talking about, if you got a perfect crystal happening, there's only one way to do that, which will give us an entropy of 0, basically, that's going to happen. Much like when we go from solid to liquid to gas, obviously we're increasing the delta S here, becoming more positive. And obviously, if we're rolling back the other way, our delta S here is going to become negative. When we do phase changes and change from one phase to the next, there is a certain amount of entropy that happens in that situation, as you may be familiar with or not, but let's talk a little bit about it, which is as you go from solid, say, to liquid, or liquid back to solid, this happens at the same temperature or different temperatures, by the way, that transition. Does happen at the same temperature. That's your normal melting point or freezing point, whichever way you're kind of going. And for example, water is 0 degrees Celsius is where that occurs. So there is a certain amount of energy, for example, if we take water as an example, at 0 degrees Celsius that is required to basically just change the water from ice basically to liquid, or if you're in liquid water, to take it back to ice. And that is what is known as the delta H of fusion. And delta H of fusion is the energy required to do the phase change, basically, between solid and liquid and backwards. And that's the energy required to do that. So for example, water, delta H of fusion is roughly 333 joules per gram, which is roughly 6.03 or 2 kilojoules per mole, roughly, give or take 1 or 2 digits. And that is the energy required to do that. And by the way, when you're exactly at 0 degrees Celsius, you have basically both phases happening in equilibrium with each other. So you have basically like ice crystals at that point. You have solid ice, you got some liquid water. It's not till you get a little bit above, again, 0 degrees that you really transition to liquid water. Not till you get a little below 0 degrees, we're going to talk about water, that you really do get into ice. So exactly at 0 degrees, you basically have kind of both phases occurring. It is endothermic, obviously, as you go from solid to liquid, right? You need to put heat and energy in there. That would give you, in terms of the heat of fusion, positive value of 333 joules per gram. As you go from liquid to gas, you have to release that energy. It's exothermic, has to be given off. The amount of energy is the same, just the sign is different, like minus 333 joules per gram. There's also energy required to do the transition from liquid to gas and backwards. So going from liquid to gas and backwards also occurs at the same temperature. And again, we'll just use water as another example here, or the same example. That occurs at 100 degrees Celsius in terms of water. And that's the normal boiling point, right, where that occurs. And it's the same idea at exactly 100 degrees Celsius. You have basically both phases in equilibrium with each other. You have basically gas and liquid sort of happening. It's kind of what happens on the surface of any liquid. You got gas molecules jumping out, and you got slower moving gas molecules falling back in, basically, or liquid molecules jumping out to the gas and slower moving gas molecules falling back in. And for example, for water, the delta H of vaporization is what that energy is referred to. So the delta H of vaporization is the energy to do that transition from going from liquid to gas and backwards, not changing the temperature, but at 100 degrees Celsius, for example, just to do that transition. Roughly for water, about 2260 joules per gram, are 40.6 kilojoules per mole. I could be just making these numbers up, but they're about close. And it's the same idea as we go from liquid to gas. That's going to be an endothermic process, which means you would need to put in there a positive 2260 in terms of water. And going from gas to liquid, you have to release all that energy, which would be minus 2260 joules per gram, which would be obviously exothermic. By the way, just looking at those values for water, it takes more energy to do which transition? Going from solid to liquid or liquid to gas? It takes a lot more energy to go from liquid to gas. And that's because as you go from solid to liquid, everybody's still relatively close to each other, right? There's a little bit more room of movement. But when you go from liquid to gas, you got to completely break everybody apart, right, to get into the gas phase. So it takes a lot more energy to do that transition. So when you are changing the phase, there is a certain amount of energy that's required to do so. How do we figure out the energy when we're not changing phases, but just changing temperatures? We figure out the energy by doing what we talked about previously, which is our specific heat equation. Yeah. So the specific heat equation would be the equation that you would use to figure out the energy as you stay in the same phase, but you change the temperature of the substance. So kind of these lines here, we're changing temperature, but we're staying in the same phase. So how does this relate to sort of entropy? The entropy of a phase change, as we'll talk about a little bit, also is affected obviously by what's going on. So let's just take, for example, as we go from solid to liquid, and we'll use water as sort of an example here. The heat of fusion needed to do that would be a positive value of 333 joules per gram in my example. So the entropy change that would occur at the fusion, or the delta S of fusion, which is the entropy change that would occur, is we would end up with a positive value here, right? As we can see that the entropy is proportional to the delta H. So it would increase the amount of entropy because it would be a positive change that's going to happen as we put in that energy. And obviously, as we would go the other way with the delta H of fusion, if we went from liquid back to solid, that would require a negative 333 joules, which means that the entropy change should start to decrease, and we would see a delta S that would be negative for that change. So there is, what do we see here? What is that process of where we go from solid to liquid? The entropy change is also affected by that delta H sort of calculation. And it will be positive or negative depending on which way you go. And there's also the delta S of vaporization that occurs right there as we transition from liquid to gas and gas back to liquid. Also, depending on which way you go, both the delta H will either be positive or negative. That will happen in this particular case. Any questions on that? Okay, so then let's talk about a different letter here, and we'll talk a little bit more about phase changes coming up in just a bit. We're going to talk now about Gibbs free energy, and look, a different letter. So Gibbs free energy is delta G, which stands for Gibbs free energy. And pretty much what the name sounds like is basically what its definition is. it is free energy that's available to do some type of work. So it's some type of energy that's available to do some type of work. We already saw earlier that if we calculate the delta S of the universe, we could use that to determine whether or not the process will be spontaneous. There are many different ways you could calculate delta G, as we will see in this chapter. One way that you could calculate delta G is this equation here. The delta G is equal to the delta H minus T delta S. And that delta H is our enthalpy. T is our temperature in Kelvin. So that is our enthalpy. That is our temperature in Kelvin. And this obviously is our entropy. And one nice thing about delta G is you can actually use it to determine whether or not a reaction will be spontaneous by calculating the delta G of that reaction. And if you calculate the delta G and it is a negative number, then that reaction is spontaneous in the forward direction. If you calculate delta G and it's a positive number, it means the reaction is non-spontaneous the way it is written. But if you flip the reaction around, it will become spontaneous. And that's because it's non-spontaneous with our reactants and products difference. But when we flip it around, our products become our reactants become our products, and basically the sign changes, and it will then become a spontaneous reaction. So negative delta G, spontaneous reaction; positive delta G, non-spontaneous reaction, the way the reaction is written. And if you have a delta G that is equal to 0, then you have a system that is at equilibrium at that point. This is one of the equations I was talking about earlier, where you do have to be careful of units. And that's because, again, we have delta H and delta S involved here. This, again, is kilojoules usually. This is joules. So once again, if you do not do the conversion, you will be off by a factor of 1,000. So doesn't matter which one you convert to, the answer is really no. But traditionally, delta G is like delta H. Traditionally, kilojoules is usually the units that are used for delta G. So delta G and delta H typically are units of kilojoules, and delta S is typically units of joules. Is usually the units that we see with them. Any questions on that? Now we're going to see a few different ways to calculate delta G, as I mentioned. Sometimes people like, which one should I use? There's like a lot of different delta G sort of values out there. My recommendation is use whatever one works with the information that's given to you. So this one would be a great one to use if you have a delta H and a delta S value given to you. This would probably be the appropriate one. We will see very shortly here, if you don't have any of those values given to you and you just have the equation, then perhaps delta G should be calculated products minus reactants, as we will see. So again, it's sort of based on the information that's given to you, is sort of how you should choose which one to use. So let's talk about the other way you could calculate delta G, and that is delta G of the reaction. And it's much like all the other ones that we've been talking about, the delta H, the delta S. We take the delta G of our products, once again, using the coefficients in the balanced equation and multiplying by the values that we see in the table, minus the delta G of our reactants, same deal, the coefficients times the value that we find in the table. And when you look it up in a table, you will sometimes, or it will sometimes be referred to as delta G of formation. And that's very much like delta H of formation that we saw. So that's just a way it's sort of labeled. The table values are labeled those things. And delta G is also very much like delta H in the sense that if you have anything in a standard state like O2, N2, just a metal by itself that's not combined, those values typically are 0. So for delta S is really the only one that sort of will have values for those type of things. Both delta H and delta G will have usually 0s for those type of guys. Again, the little knot means basically go to a table, standard conditions. We did it under these type of conditions as we were just talking about. 1 atmosphere if it's a gas, 1 molar if it's a solution, and usually the temperature is 25 degrees Celsius. So that's a good way to kind of think about that. May not be correct in all aspects, but that's sort of the way you kind of think about it, what that little knot means. All right, so why don't we try one here, calculate the standard free energy change for the following reaction. Standard free energy is the delta G, by the way, and I think you have the values on your table, I think. Hopefully they're these. And is the reaction spontaneous at 25 degrees Celsius? So take a moment, see what you get. Okay, so we're going to be looking for our delta G naught of this reaction. So in this case, we're just given the reaction. So that pretty much just signal use it, go to the table probably and look up the delta G values is probably the best approach. Our delta G of our reaction here, again, going to be our product. So in this case, we got 12 CO2s. Each of them is minus 394.4 kilojoules. We then also have 6 waters there. So 6 times our value for water minus 237.2. That takes care of all of our product side. We're then going to subtract all of our reactant side, which would be 2 times our C6H6. Looks like a 124.5. And that'll be plus 15 times the value for O2. I don't see the value for O2, but the value for O2 here should be 0 as it's in a standard state. So again, delta G or delta H, anything in a standard state would have a value of 0 for delta G. So that's going to be 0. It's going to get us here. Looks like a minus 6405 kilojoules in this case. Yeah. Any question on that calculation there? This delta G value is negative or less than 0, which means that this reaction is spontaneous or non-spontaneous. Reaction is going to be spontaneous because our delta G value here is negative. It means it is spontaneous the way it is written. We would expect this reaction to proceed to the product side in this case. Yes. Any question on that there? So in this case, obviously, we weren't given any delta H or delta S values, so we didn't want to use that equation. This would be, again, the appropriate equation there to use. Now, speaking of the other equation for delta G, as I mentioned before, sometimes you will be given some questions where they will not ask you or give you numbers or anything like that. They will just ask you, will this reaction be sort of spontaneous or non-spontaneous? And you can make some pretty good predictions just based off of the actual equation. So let's take a look at that there. So if we look at this equation, depending on sort of the temperature and signs that we see for delta H or delta S, we can make a pretty good prediction as to whether or not this reaction will be sort of spontaneous or non-spontaneous under those conditions. So for example, here, if we have a delta S that is greater than 0 and a delta H that's greater than 0, that means that both of these guys here would be a positive value. That means that this reaction would be spontaneous at only high temperatures. So you would need high temperatures to do that. So why do you need high temperatures? Because again, delta H here is in kilojoules and this guy's in joules. So in order for the back part of this formula to overtake it, because the temperature should be a positive number, it needs to be a high temperature, and that will give the back part of this formula a higher number than the front part, and that will result in a negative delta G. If you had a low temperature in this situation, frankly, this guy will overtake this guy, and you'll have a positive number on both sides, and that will end up with a positive delta G. If you have this equation and you have a delta S that is positive and a delta H that is negative, which is an exothermic situation, what happens now? Does it matter the temperature? Well, in this situation, any temperature you put in here is going to result in a negative number here. And this guy is already negative, which means no matter what you do to it, your delta G value will always end up being negative in this case, which means this reaction would be spontaneous at any temperature pretty much. So any temperature, this reaction would really be spontaneous. If we look at this reaction or this equation, and we have a situation where we'll go to this box here. We have our delta S that is less than 0, which is negative. And we have our delta H, which is a positive number. This negative number will turn this negative into a positive, which means no matter what you do at any temperature, your delta G here is going to end up being positive in all situations. And that means that this reaction will pretty much be non-spontaneous, right? At any temperature. I guess I should write spontaneous, right, for these guys. And the last sort of situation that you could have is if you're looking at this equation and we look at our delta H and our delta S values, we're to this box here. We have our delta S, which is less than 0, which means it's negative. And we have an exothermic delta H, which is also negative. And that means that these two negatives here, once again, are going to turn this into a positive. So as long as the temperature is a low temperature, that will keep this part being less than this part. And that will always result in a negative delta G at low temperatures. It will be spontaneous. So a lot of times in this thermodynamics chapter, they'll give you a lot of these sort of questions like no values or anything. They'll just go, hey, this is positive, this is negative. You know, under this temperature, do you expect it to be spontaneous or not? You clearly can make up numbers and toss them in there if you wanted to into the equation, but sometimes you'll see a lot of questions like that where there's kind of like no values. They just kind of give you negative, positive, and what do you think going on there? Any questions on any of that there? All right, I think it's a good stopping place actually.